going on. Thank you everyone for attending, both in person and online, and if you're watching the recording, which we have permission for. So it's our distinct pleasure to have Shri Kulkarni speaking to us for the CITA seminar this week. He's been visiting us for the past week at Toronto. And what I really love is that if you go to his website and you go to his CV and bibliography, there is a page that says colloquium organizer in a hurry to introduce SRK at a colloquium, no time to prepare, and it just links to a biography, which is brilliant. But I will just give the abridged version because even that is quite long. So Shri's the George E. Hale Professor of Astronomy at Caltech. He was director of the Caltech Optical Observatories up until 4 years ago or so. He's primarily known for looking at all kinds of cosmic explosions. But as you might be aware, if you attended his Astro Colloquium on Wednesday, or if you were at our cosmology lunch on Friday, his interests are quite diverse. Having given us a very thorough accounting of the cosmic far UV background on the colloquium downstairs last Wednesday, I think we're going to switch wavelengths. Is that right, Shri, towards the IR?
Yes.
All right. So I won't delay any further and let Shri get on it with it.
Okay, so this is a bit of work in progress. So as I told some of you on Wednesday, after I stepped down as a director, I said, I want to end my career doing something very different. I thought, didn't want to raise money, didn't want to lead large team. A theorist. And even I showed you my certificate, I hope you remember it. I'm a certified theorist now, by no less than from Harvard and no less than Avi Loeb. I know Juna is already impressed. Okay. Okay, so this is a work in progress because I only started this on July 15th after listening to the press announcement from JWST, which I had not planned to attend. It's a great mission, but I thought it's for the next generation. And the last thing I like to do is join any popular movement. But my colleague Chaz Bachman said, look, it's really a great thing. You should watch this. So I listened to it. Then I said, well, in my new found role as a sharpshooter theorist, I listened to it. I said, oh, there's obvious stuff. There's early galaxies. There's exoplanet atmospheres, star formation. I mean, I'm not going to be thinking a bit about that. Anyway, at the end of the day, July, I said, okay, I have a nice orange tree in my backyard in Southern California. A glass of wine. I said, what is it that no one's thought of that can be done with JWST? And nothing happened. And then I had another glass of wine, and then suddenly it happened. Then 2 days later, I think I had the thing. Then I checked with Bruce Drain to make, he's my ISM, because I haven't been in this field I need some check whether it's all right. And he was skeptical. I said, and then after about a month, I convinced myself this is interesting. I finished the paper. So, that's what sharpshooters do. They find the next little thing to bet on. Okay, so it's a bit unorganized, but you learn all about the warm ionized medium. But before I go into that, since we have the CITA director here, and who's a powerful authority in the University of Toronto system, I wanted to, if you go around one of these streets, there's like, something, the impossible is possible, obstacles are motivated. Well, that's all from University of Toronto. And it says, defy gravity. Yeah, and anyway, so I thought there's no way if you really could defy gravity, then we can't have CITA. It's the university has to choose between CITA and this poster. And there's a very simple way to fix this problem, which is we just add okay, so I'm hoping that Chris will take a ladder and start just a little graffiti, just a little bit, and that would be the right thing. Now there's a compromise here between reality and aspirations. Okay, with that, let's move on. Okay, the beginning. So I'll assume that many of you are not very familiar with the galaxy. I mean, it's not a very popular subject, and in particular, interstellar medium of the galaxy, that's even less popular. It used to be popular 40 years ago. Okay, so the beginnings of what we now call as a warm interstellar medium actually lies in low frequency astronomy. It goes back to literally, I believe, 1962 or something like that. In Tasmania, so this shows the spectrum of the galactic radio emission between 10 megahertz and 1.5 megacycles per second, and which is possible. When the solar activity is low, you can actually go down to about 2 megahertz. And if you look in the inner galaxy, as shown here, and this is the full paper, by the way, this is it. This is the one-page Nature paper, which is, I think, the right way to write these things instead of this long stuff people do. Here's the data. It shows that the spectrum turns over, and the explanation that came later, these are the observers from Hoyle, and was that this, in fact, is due to free absorption in the galaxy. And that's this paper here, just a few months later. And as far as I know, this is the beginning of the warm ionized medium, and some of the numbers they got are still amazingly right. The Coriolis density, or mean density of 0.1, meaning the true density, then the amount of power you need, and attributing to OB stars. So in that sense, nothing has really changed from 1962 to the year 2022. Okay. But, it's one thing to write, slap of a theory paper, but in the end, it has to match up with reality. So the rest of the talk is to tell you about this medium. So that was in the 62. Then by end of 60s, the pulsars were discovered. And every pulsar showed this sort of a dispersion where the high frequency, this shows the arrival time of a pulsar. Now, the high frequency, this at the top of the band would be about, looks like 390, 400 megahertz. And the bottom of the band is about 320 megahertz. You can see that the arrival time is, it arrives at the highest frequency first in this band, and then goes down as 1 over frequency square as delay. And that's exactly the dispersion law you expect in cold plasma. When you say cold plasma here, it just means the temperature of the plasma is less than MEC squared. Okay, that's what we mean by cold plasma. Okay, so that again requires this is perfectly consistent with the with the idea of having a diffuse ionized gas. And the next one is in the early 70s, Ron Reynolds, I would say, sort of more or less single-handedly started this field, though of course H alpha observations for H2 regions were around, but he brought in Fabry-Perot methodology, which really allows you to go to an emission measure well below Rayleigh. Okay. And of course, this is H alpha, and which you get from 3 to 2. And I discussed a bit of what happens in this 2-photon emission last week. Okay, so at Wisconsin, Reynolds began a program late 70s, and which has basically pioneered and established H alpha emission from the galactic interstellar medium. It is the WAM, the Wisconsin H alpha mapper, I believe it's right now in South America, in Chile, is a Fabry-Perot imager, which is a wide beam, it's a degree beam. So because when you want to do surface brightness, which is what this experiment is, what matters, as you know, is A omega T, actually divided by resolution, if you want to be very exact about this. So if you want that metric to be as large as possible, you make A large. If possible, you make omega as large as you can, and you make the resolution as small, as large as it's in the denominator. So the resolution for Fabry-Perot is quite high. I think in this case, maybe 30,000. And the beam is very high. Degree by degree is a very big beam. So you can routinely, with very modest integration, achieve 1 sigma of 0.1 Rayleigh with this system and image the whole sky. And the workhorse bands or H alpha, primarily, there's a whole image of the sky in H alpha. And many thousands of square degrees have been studied in forbidden nitrogen N2 and forbidden S2, which tell you something about the temperature of this gas. There are many other optical lines, which we'll talk a bit, but they have not been as well studied by the WAM project because it took a long time for them to finish the H alpha survey. And which is a pity because you'll soon see that there's a tremendous information if you could just have WAM and continue to image the sky in these other forbidden lines. Okay, so the warm-ionized medium became established, I would say, by the McKeough-Stryker model at that point. That a specific idea what this is. This is the ionized envelopes of what would be called as the warm neutral medium, which is a neutral phase of the two-phase model. And these are the currently accepted numbers, maybe 8,000 Kelvin, true density of 0.2, which includes electrons and protons, and the ionization fraction of 90%, though we'll come back to the latter, it's not so clear, but this is a typical number to carry in your head. So I hope that you realized already there is a difference, and this is, by the way, a picture of the H alpha sky from the WAM project. Yeah.
So Shri, just thinking about the warm ionized medium, and we're thinking about this in the local volume mapper. What do you think is the relevant sort of substructure, right? So you have the scale height here, and there are some sort of characteristics of the medium generally, but when you think about any kind of population of other celestial objects, there's some kind of fundamental structure here. And here you're just looking at gas, but even in like the intergalactic medium, there's the filaments, like there, what would you say? I mean, is the fundamental structure in the warm ionized medium just characterized by the turbulence, or what would you say, like when you're physically picturing this in your mind as you're manipulating it?
I would say you don't know this, because what you can see is at 1 degree and above, that's the map. Okay, then if you wanted to point like pulsars to a certain distance, yeah, but you have 3,000 points, and at varying distances, so if you say what is the structure function to be, no, we don't know this. We know it from degree and above, but that's not the interesting scale. I think you really want to start from the outer scale at that point. I think, in fact, probably, and that's the point of this talk, is that I think we are now on the verge of actually. So if you really want to do this, and I've not yet made up my mind, because I thought I got distracted by this JWST thing, but I've already been thinking, if I had to redo WAM, what would I do different? But we can come back to that later. That's a hardware project, and I'm trying to stay away from going back to my old self of inventing projects, because then you start doing them. So okay, and if you want to be a theorist, you shouldn't think of such things because they're a distraction. Okay, the warm ionized medium is also there in other galaxies, notably our own dwarf galaxies. You can see, in fact, this is taken in H alpha, and it fills much of the LMC and SMC. It's also there in more regular galaxies. This is Rich Rand's thesis, where he found, in fact, the warm ionized gas actually extends quite a bit of a scale height. This is in H alpha. Similar thing was seen in sulfur 2. Okay, so in our own galaxy, the warm ionized medium is about 10 to the 9 solar masses. The neutral phases of atomic hydrogen adds up to be 5 times 10 to the 9, maybe 4 times 10 to the 9 solar masses locally. I'm sorry, globally, and yeah.
What is now thought to set the outer boundary?
This over here.
Oh,
I mean, yeah, that's a sort of a very special topic of how do you go from this inner halo to the CGM. So I think I don't have any, I would say, learned opinion yet on that, but many people are interested in that. Okay. And it's a computation, obviously, from the stellar lights leaking to the intergalactic flux you have. it's a thing you just do observationally, as best as I can tell you.
There's happening is also high, so it's not just the radiation balance, it's also the burial shocks and everything. You have the temperature structure is different at those scales.
Yeah. Okay, so good. If anyone is holding a quiz for grad students in one of these things, and what they call qualifiers, trap them in, and they think that's H2 regions. In fact, they're bright. They process more H alpha photons, but are only only less than a tenth of the warm ionized gases in H2 regions. And of course, then you ask them why, and then you can lead them down a rabbit hole and make the exam more interesting. But anyway, okay. It's a joke. Okay, so the filling factor of this gas is substantial. If you just confine to the lower disk, it's about a quarter. And in order to power, to ionize this, you need about 6 of the OB star Lyman continuum in the, to power it. The big open questions, I mean, this has been known, as I said, in some sense, arguably from the Hoyle and Ellis paper, but is how does this Lyman continuum reach nooks and crannies in the interstellar medium? Okay, this is a very hard, this is not a, this is now a detailed numerical problem, because it's not a question of is there enough energy? Yes, but it's, if you just make this in any reasonable, if you don't put in some sense, some fractal structure or a lot of tunnels and so on, you can't get this Lyman continuum to a scale height of 1 kiloparsec. Okay, but there's a clue, and or at least in how basically you have Lyman continuum that propagates through neutral medium, and of course, if it is homogeneous neutral medium, you can solve this. This is a homework problem, and then the answer is that you won't get the warm ionized medium. But the spectrum of the field that is incident is a big clue to what's happening with this modification of the spectrum as it propagates. And here you can see that unlike H2 regions, the warm ionized medium is not 99.97% or whatever highly ionized. In fact, it's probably 90%, maybe even arguably lower than that, but maybe we'll just, until we go back to it, we'll assume it's 90%. Okay. And then a related question is, what is the ionization fraction of helium? Okay. And the reason that's important is that the EUV field, the value at 13.6 EV and above tells you the ionization of hydrogen, but 25 EV and above tells you what is the ionization fraction of helium. So it's just a crude metric at these 2 points of understanding the slope, if you wish. Okay. And so we'll come back to this major question at the end of this talk. Okay, since I think I can rightfully assume that subjects like the Galactic ISM and atomic spectroscopy are very musty subjects, so I thought I will do a little bit of a review of this. And for that, if you want to say, how do I look at hot gas? It's actually useful to understand what nature offers us. So if you want really the very hot gas, which is the million Kelvin hot ionized medium, you have to go to the FUV, and you have to use basically these lithium-like ions of these abundant elements, carbon, nitrogen, and oxygen. And as you can see, they're all in the FUV, which is why you really want an FUV mission. If you then say, well, it's slightly in between, less about 10 to the 5, then it's still in the FUV for carbon 3, nitrogen 4, oxygen 5. But then some interesting things start opening up when you go to more electron systems. So the first line that opens up here, the C+ line, it's a fine structure line. It's a fine structure long wavelength line at 157.6 microns. And this is a great value if you're doing extragalactic studies. It's not the best line to study ionized gas because it can arise in many medium, okay, because it can arise in anything which is, the temperature of this line, or the expressed in temperature units, I think is only 92 Kelvin, so it's easy to excite it. Okay, but finally, when you start getting into these abundant elements which are lightly ionized, like nitrogen 2 or oxygen 3, okay, you start getting to see these optical lines that are developing. But and the fine structure lines still continue. When I say fine structure, usually it means long wavelength, because that's where much of the focus has been historically. Okay, any line which is, spin orbit interaction in the ground state is the fine structure line. Okay, now these are the traditional optical lines, and they come in two flavors. Now, one is let's take O2 for example. Okay, so if you go from the ground state to the first excited state, okay, that's usually called a nebular line because these were first seen in H2 regions. But if you go from the second excited state to the first, those are called as aurora lines because that's how they were discovered first in the aurora. Okay, so if
definitely change this terminology.
well,
It's like so obnoxious, right?
well, no, I like it. This is like a secret thing that the theorists pull. They'll get so confused as soon as they're auroral, they'll drop out, and okay. It's like the guild. Okay. Anyway, then you have the transauroral lines. And anyway, if you read these old books, you'll find these nomenclatures. So just so you know that what it is. And you can see, you can take the ratios, you can get the temperatures. If it's a doublet, you can get the densities, and that's all there is to it. Okay, it's not all that difficult actually. Okay, but for the first time, if you can see with neon 3, you're finding these fine structure lines which are no longer in long wavelength. 150 to 200 or 300 microns. That's pretty long wavelength. It's a bit hard to get to actually. Now in neon 3, you see that the fine structure line is actually now at, in this case, 15 microns and 36 microns. Okay, so these are the mid-infrared fine structure lines. They're not as well known in this sort of business. They're very well known if you're studying, star-forming galaxies and so on. But in the study of the diffuse gas, they're not all that very well known. Okay, well, I just want to show them many fine structure lines here. You can see, and the last one would be, in sulfur 4. Okay, fine. I think, there's some more sulfur 3. Okay, I sort of like these sort of, if you want to do this subject, you really have to become very familiar with this Grotin diagrams and love each one of these lines. Okay, but now this is all well and good. And I have to make sure that you understand the technical difficulty here is if you want to study your own galaxy, that is the hardest problem. If you want to study another galaxy, especially which has got a redshift, let's say, of even a minor thing like a few thousand kilometers a second, not so bad. And the higher the redshift gets a little easier. So it's not, so there's a big difference between, for example, something you people know here, which is the dragonfly, and something like WAM. Okay, if you want to study your own galaxy, you can't use narrowband filters because of the night sky. The night sky is replete with the aurora lines that Junai doesn't like, but that's exactly what you see when you go. Okay, it's blazing. If you go to the Arctic regions or Antarctica, you'll see them, in a dark night, and if there's enough sun is active, you'll see them blazing away. And in particular, I draw attention to this oxygen line, which is very bright. And it'll play a role in this talk later. Okay, so even though you want to study the forbidden lines of nitrogen, oxygen, whatever, unfortunately, the Earth has that by the spades. I mean, it can be like 10 to the 3, 10 to the 4 times larger, and therefore, when you do some narrowband experiments, you sort of you can play a little game with the redshift and choose properly. But with a galaxy, you have no choice. Okay, so as an example for you to appreciate how difficult this is, here's on the left forget the velocity scale, it's arbitrary because when you do Fabry-Perot, the 0 point is not set. You have to understand that, but let's ignore that technical thing. We see a very narrow line. This is around H alpha. Okay, see a narrow line here. It's narrow, it's bright, and then you have something else. So this we know is actually geocoronal H alpha. Okay. And you know that because it has a certain velocity, namely its topocentric velocity is 0. And if you come back a few months later, it'll still be topocentric 0, but the galaxy would have shifted. Or if you work in VLSR, it would have changed to you. So we know that. So you can model this and you find this is the rest of the galaxy, all of the galaxy put together. And so you got to subtract this part accurately. So the understanding the 0 point is critical here. Okay. Okay. And last Wednesday, I introduced this. I made a mistake here. There should be a 4 pi here. Okay. That's 10 to the 6 divided by 4 pi. Okay. Okay. So okay, this is a bit too detailed here. Basically, and I showed the spectrum and the same thing here. The sky in the optical band is about 2 Rayleigh per angstrom. Okay, like for example, here's H alpha again, back to H alpha. Where is it? There it is. And roughly speaking, when you convert that to Rayleigh units across this whole band, from 4,000 to 7,000, it's about 2 Rayleigh per angstrom. And that's why you want very high resolution. Okay, because the higher the resolution, then you can start beating it down, and you have to overcome this. Okay, so the modern methods now, we still have, even though the game started with the free emission, this is not, even though I list this on the top, this is not yet materialized actually. One of the things that I hope with LWA and LOFAR, that this will become more routine. This is that you really need to go to very low frequencies to start doing this stuff. Okay, but now we have pulsar dispersion measure that's routine. It's supplemented by FRBs. Rotation measure, that's pretty standard. And in particular, it's very good to study fine structure because you can make images with the interferometers. Then I talked about H alpha, and the main problem here with all the optical line studies for galaxies that they are done at a rather large angular scale. Radio recombination lines, I'll only mention, we'll come back to that because that's a big clue for helium ionization. And then 2-photon continuum, which is my talk last week. And finally, we'll focus a bit more on the resonance lines and far infrared. Okay, resonance lines, which has been the mainstay. And here we'll focus on sort of, I would say, newish. These lines have been known, but they're not being used to study the warm as medium, which is the mid-infrared fine structure lines. And the other one, which is about to start, which is high spectral and angular resolution with optical IFUs on large ground-based telescopes. And these two are related because these really require large telescope. The first one is possible because JWST. The second one is possible because of IFUs on, especially the cosmic imager, which unlike MUSE has a very high spectral resolution. That's key to this thing. Okay, so let's start off with the first one. As I told you, I sat down and thought, what is it no one could have thought of this? And the idea here is that JWST has a integral field unit spectrograph in both sides, which is the mid-infrared channel and the near-infrared channel. And let's focus on the MIRI system, which is, and this have an entrance of about 3 by 3 arc seconds to 7 by 7, depending on the wavelength range, which is an extremely small field of view if we compare to a degree by degree of the Wisconsin H alpha mapper. On the other hand, the Wisconsin H alpha mapper is $1 million, and JW is 10 to the 10. So you can see that it should do a bit better. And it turns out to be surprising that even with this narrow field of view, you can actually detect diffuse emission lines. Okay. The key thing is it's got a large collecting area. So I told you A omega T over R. Now compared with Spitzer, which A was small, R was small, JW has large A, and the resolution for the IFU is quite large. It's about 3,000, which in this game is quite impressive. Okay, so one advantage of teaching is you become familiar with these things, so you can actually go through all the growth trend diagrams and make a list of things that will be of interest to this topic. And these are the lines of interest, okay, which are both which are accessible to the MIRI IFU system, and are also, you expect them to be abundant in some reasonable fraction of them in the warm as medium. Okay, just so that you understand, it's if you want to do ISM, you should have a fairly good memory for ionization potential, or at least you should have some idea. So let me make sure you We all remember this. And so to go to neon 2, it's 21.6 eV, which means neon 2 is closer to helium. So if you want to understand this, as I said, the goal here is to understand the spectrum of the Lyman continuum that is shining upon this warm ionized medium. And so neon 2 is good because getting closer to helium, which is, I forget, 25.4, I think. I should remember a bit better. Sulfur 223, that's even better. Sulfur 3 is almost there at helium. Okay, and the other one that's useful is argon, which is closer to nitrogen, which is closer to hydrogen. Okay, so the game here is to start using these in different states and peg these two fluxes, the brightness there. Okay, in order to do this sort of any of these background diffuse studies, you must understand the background because that is what's limiting the things. Okay, so here's a JWST background model. And since there are not many grad students here and I don't embarrass the postdocs because then they'll get more embarrassed, but otherwise if the grad students I'd ask them to, in the colloquium, ask them to explain to me where the two humps come from. Anyone wants to do that for me? Okay, there are two humps here, so let's focus. There's a blue, there's one hump here, centered about 1 micron. There's another hump centered around about 25 microns, and that's a part of the background. Oh, the red one here is just the telescope is getting hotter, even though it's cooled. It's just the Rayleigh Jeans tail. It's the sorry, yeah. Okay, and how about this? Oh, wait, you're neither of you are postdocs here. Okay. Okay, so this is zodiacal dust in reflection. Okay, the albedo of Zodi dust is about half actually in the optical. So this is Zodi in reflection, and the other half is absorbed, and that gets heated up, and that's gives rise to fairly warm emission. So you can't escape this background, even with JW. You really need to send a mission to Pluto and beyond to start decreasing these backgrounds.
The main investigation about warmer zodiacal dust was Brian May from the band Queen. That was his PhD thesis.
Okay. So there it is. Okay, now this is it's an amazing instrument, this MIRI MRS instrument.
Can I just ask a dumb question?
Yeah.
With things like COS, for example, was there never any actual direct measurement of the UV hardness in like the background hardness from in the galaxy? Like, were they not able to
Which cost or few? What are you talking about?
use or COS for any one of those prior missions? Like, do we really, you know, so your point here is that you're going to basically get a measurement of the background spectrum, but were there no attempts to do that directly with the?
Oh, that's very hard. There's a
No, it's hard, but they
mission that flew 2003 called Minisat 01. It carried two spectrometers in the FUV below. First one was 900 to 1100. The other one was maybe 11 or maybe 900 to 1200. No, 13. The other one was 13 to 1700. And no, you can't find this in continuum. It's all done through lines. Okay. Okay, so this MIRI MRS is really amazing. It covers 5 to 29 microns, and has but you need 3 settings to fully cover this range. And the average spectral resolution is about 3000 lambda or delta lambda. Okay. So anyway, the calculation I did after sitting around in the second glass of wine was actually, you look up the things and you compute what if you know the emission measures, what is the expected these things. And I was really surprised. The final number to remember is the signal to noise ratio. And the signal to noise ratio after an hour of integration with MIRI MRS system is pretty good. In emission measure 1 is a typical number. If you look straight up out the galaxy, the emission measure is 1. Okay, so it's a nice, convenient localization, normalization. Well, these are pretty astounding numbers. Look at this. Well, now, of course, this times the ionization fraction, but even if it is like you put a half or whatever, you suddenly realize that this is actually detectable. Okay, anyway, so charged up thus, since my friend Chaz asked me to watch the thing, I called him up a week later. I said, Chaz, just find any data set, and it has to be 1 hour long and away in the, and doesn't even have to be in the galactic plane. I predict we'll see these lines. So he works with the MRS team, and he went and got some HD something, some very bright naked eye star. And there's an at high latitude, and it's this, the star is some, it was done for photon, calibration. It's somewhere here, and this is a large image of the sky. Okay, this is in tens of degrees. Okay, don't be misled. And this is an H alpha map, and in the bottom here, and it turns out it's a long story. You have to divide this by 24 to get the emission measure. Don't ask me why, but there's a bug in the WAM repository, which I found only later. Okay, so that it's in the middle of nowhere is all I'm trying to say. It's not behind some well-known planetary nebula like NGC 6543, which is also observed to do the 0 points on the velocity calibration system. Okay, so here's the MIRI-MRS thing, and there are 2 pointings. This is the star itself, HD 166433. You can actually see with naked eye, and JWST spent 10 hours on this. I can tell you that. It's pretty amazing, actually. They must be really trying to nail down the photometric conversion. And this is so-called, what they did was a background field just to be sure that they could subtract in case there are nuisance things like the galaxy. And we'll just look at this. It's only a 20-minute exposure, actually, of this, about a few arc minutes away from this star. And there it is. Okay, now don't be alarmed. First time I saw this, I thought, God, it's a dog's breakfast. And it's because this is just, first month. They've been having huge calibration issues. But you know the wavelength. In fact, I know it's even in the spiral arm, it's in the Perseus arm, so it's slightly negative. If you look at the eye, it is slightly actually negative when you compare to the rest thing. So this is actually a neon 2, and so if you apply a simple Fourier filtering, what's really happening here is that there's sort of some sort of I don't know. There's a lot of 1 or F noise. Maybe it's the readout system, and the other one is a fringing. So after doing some Fourier filtering, okay, of the spectrum, you can actually see beautiful detection of neon 2. Okay, so now emboldened dust, you can see now sulfur 2, sulfur 3 is detected. Anyway, I bashed through the paper. That's a nice thing about big missions. You don't have to be that smart at all. It's like big missions are launched, it's like gold on the floor. You just stumble and you fall down and you say, oh my God, there's a piece of gold here. Okay. So now let's get on to the, anyway, so now the story here is simple, that, and this is the part I really love. There's a JW is going to be used to study, redshift 10, 12, whatever galaxies. All this, I have many friends who do this sort of very popular stuff. The part I like it is I told them, what, no matter what you guys do, the first thing you'll see is right against your nose. It's a galaxy. Ha, ha, ha. Okay. Anyway, so every JW observation of these galaxies will find the warm ionized medium, whether they like it or not. Yeah. Line widths, no, not much, because the line widths here, you can get the centroid, and it looks like the centroid is minus 30 kilometers here, which is about right per second, because the H alpha is also maybe at minus 40. The widths, these are very crude lines for, so this is only 3,000. So it's what? The widths of 3 times 10, 3, 10 to the 5. So it's a line widths of 100 kilometers, not very valuable for studies of the galaxy. Okay.
Do you see any evidence for varying ionization structure?
Oh, this is it. I showed you the one spec, 2 things I got. I verified it's also seen in the star, but there's scattered light. We have to solve for that. But the brightest line is seen there. And as a theorist, you sort of do the concept, then you leave it to the observers to clean up the mess. See, I'm in this new mode of leaving it to others. Okay. But now let's go into the inference with this one spectrum we have. And so in particular, it's the ionization of, oops, what happened here? So anyway, so I just to, just a minute, I'm a little puzzled.
But basically, you can pull that out of every JWST observation, certainly all the calibration. So you'll be able to get a patchiness and
Absolutely.
you'll be able to actually piece together something like a structure function, sort of.
Yeah, so in this particular case, even though the two observations, the star and the off, are separated by 2 arc minutes, I can tell you roughly it has not changed much on the 2 arc minute scale. Yeah.
Right, but there's like an archival proposal to do it in.
Yeah. Yes. Absolutely. Every miri-MRS observation, more than I would say 20 minutes, you'll start seeing this line. Not just the line, the whole family. Okay. And don't be those of you theorists, you look at this stuff and say, oh my God, it takes about 2 or 3 years to actually learn how to reduce IFU data. But since it's a $10 billion mission, we can speed it up. Maybe it'll only take a year. Okay. But after that, it'll be pretty straightforward. Okay. I just put together this talk more as an informal thing. So I'm not sure the exact order, but let's now, I'll in the end synthesize all this here.
When JWST, do they release when you get your data, do you have to do is there some pipeline reduction that would spit these things out as part of the standard pipeline, or do you have to do some special reduction?
I took what's called level 3, which means their highest level processing, which they give you a cube, RA deck and intensity in RA deck in arc seconds, intensity in megajansky per steradian.
Like how much work went between the thing that you downloaded and getting the intensity of the line, like the
main work was, I don't know how to use Python.
Okay.
I had to find someone to convert that, and it's a lot of Python stuff. It's MATLAB after that, maybe an hour. That's about it. Okay, so it's not difficult. That reduction is bad. There's no question. All that Fourier filtering, that's nothing. It's just like there's zero basis for the base. There is no physical model there. I looked at it, and from my eye, I could see this fringing, and the other stuff is probably some very bad read noise, 1 or F noise, and so I had some idea, and that's all there is to it. Anyway, so yeah, so this is not what I'd call as a ab initio, quality reduction. I knew what I was going for, and it's helpful because I'm looking for delta function. So this won't work if you're looking at resolve a galaxy with a rotation and so on, because then you'll filter away your signal itself.
Right, but here all you care about is an intensity on a sight line, and you want that as densely sampled as JWST will give it to you.
That's right.
So,
that you'll get. So you'll just
have that.
Yeah. So now let's go into the, okay, so it's now, as I told you, I initially moted by saying these other ions, and they start telling you something, or if you can start doing the ionization fraction, the continuum level, right? Okay, so let's understand a bit of the physics here. Why are we interested in the ionization fraction of hydrogen? Well, that's a key parameter, okay? So what is the fundamental physical difference between the warm ionized medium and an H2 region? And the answer is very simple, that the main thing is each of these ionizing regions you can characterize by the ratio of ionizing photons, the density of the ionizing photons to the density of the hydrogen atoms, okay? And it has many names. It's called ionization parameter. It doesn't matter. That's all there is to it. So once you know this ratio, the difference is in H2 regions, they're very photon rich, okay? And the warm ionized medium is very photon poor, and which is why their appearance changes and the ionization fraction changes. Okay. So the question, it's been around for a long time, is what is the ionization fraction of the warm ionized medium? And it's not been, you'd think this is, well, it's a basic question. You think we'd know the answer to this. The answer is, unfortunately, I don't think we know it in a very firm way. I think everyone in this field would agree it's surely above 50%. I'm not exactly sure why someone would, I would say everyone would agree. I can tell you surely about 25%, but that I don't think anyone would question. And someone says likely below 95. Well, we really need to do a bit better job than this. This is the most fundamental parameter of the warm ionized medium. The traditional approach has been to use oxygen to H alpha. Now, for some of you who don't do this sort of stuff, this is sort of getting so arcane and so specific. But trust me, all this stuff that some of you are doing, like it's galaxy simulations where you put in things, star formation and all that. This is, if you don't know this stuff, it's just a very simplified model of doing. So anyone who does star formation history on sort of kiloparsec scales really would like to know this answer first, okay? But so it is worthwhile going into this arcane stuff is all I'm telling you. So the traditional way has been to use the oxygen as a way to, as a surrogate for H alpha. And why? Because the ionization potential of oxygen is 13.618 eV, whereas that of hydrogen is a little bit less than 13.6, and the difference is 200 Kelvin. So oxygen ionization potential is 200 Kelvin above that of, so, and it so happens that it has a very strong charge exchange cross section. Okay, so the combination of the two makes oxygen will always follow the ionization fraction of hydrogen. Okay, so if hydrogen is 50% ionized, so will oxygen. So by just looking at O1 in this medium, you could actually then measure the O1 to O2 or O1 to H alpha. You'd measure this. Okay, is that clear? Okay, however, there's a problem. So again, as I said, if you want to study the galaxy, so let's understand what this problem is. Yeah. So, okay, this is, okay. The problem here is now to understand, this is air glow, okay? So here's oxygen. Oxygen has two lines, and many of these things are doublet. You always choose a stronger on this case. So it's a 3p2, this is a 6300. Well, here it is. This is in Rayleigh. So sometimes the oxygen thing is at least always about a kilo Rayleigh, sometimes even more, okay? And remember, we started off with the Rayleigh per angstrom, and suddenly we're looking at this. The Earth is incredibly bright in atomic oxygen, okay? And it doesn't help if you use the other line, the somewhat secondary line. Yeah, the background is smaller, but so is the height here. So you're looking at some, in contrast, by the way, these are all terrestrial oxygen, okay? If you look at nitrogen, there's only about 100 really, okay? So I was very, very puzzled because because the ionization potential of nitrogen is 14.6 eV. At the rate we are asking, it doesn't matter. We don't need it exactly equal. You know, we want to know what is the radiation field around 13, a bit above hydrogen and a bit above helium. Whether it is just above or a couple of EV doesn't matter. It's within KT. Okay, so I was really puzzled. I thought, why is it there's such a historically no one's been using nitrogen? So I called up Ron Reynolds, the father.
Why there's so much danger because there's no ozone equivalent? That's not the O1
I don't know. I can fill. Let's say maybe I don't have this. Okay, let me tell you that story. So first, I called up Ron Reynolds, okay, who's retired, and he said, "Oh, retired." I said, "No, you have to go back to your notes." And so after about a month of badgering on him, he eventually, and then he called me up to thank me for, asking him to look into these things. And it turned out that he just thought oxygen would be better. It's just that he never tried to look into the details, and so that got me very interested because Ron is really like the father of this field. And ESO has an amazing program that they have I guess they're well funded, but they have an aeronomy group. The people who are aeronomers who use all the archival ESO data, both force and with the equivalent of high-res spectrometers to study the atmospheric lines. So I'm now in touch with one of the young people there. And it turns out this nitrogen is even more curious. It's not only not much fainter, but it's also highly time variable, whereas oxygen is not. Yes, oxygen is time variable. It just goes from being bright to super bright or super bright to bright, depending on when the sun has set and all that stuff. But nitrogen actually sometimes just practically disappears, okay, at least at Paranal. So, I would say one of the things in this is that I'm absolutely sure that this is a historical oversight where someone decided to go after oxygen, and when in fact I would say that was a mistake because it's a much harder measurement. So we should, I think, study nitrogen instead. Okay. Okay, sorry, here it is. Okay, so if you want to study nitrogen, okay, so I'm saying we should go for this line. This is the stronger line, this 5200 angstrom line. And you can then I worked out this ratio of that to H alpha. Already I can, this just with one data point that exists in literature, but I think this is the way to go. This will really actually, with optical techniques, will directly settle this question. Unfortunately, this requires either reviving WAM or actually building a new version of WAM. And there this is a little perhaps inappropriate audience because there's so much fun technology of what do you do in the year 2022 for Fabric Pro compared to 1982. So I think I know a way to build a super WAM for like $1 million actually, and it'll be really fantastic. But let's okay. Then how about helium? Okay, now helium. Remember that hydrogen and helium both have recombination lines. Okay, the standard ISM question is you ask a poor student, okay, given this detection by LOFAR, what is the equivalent helium line? Okay, it's actually easy calculation, just certainly reduced mass and all that. But helium, for a long time, radio studies of the diffuse ISM have always found helium abundance. The equal to is a very strong number, but it's very small, 13%. Okay, helium is, which suggests that this radiation field actually softens as it propagates and at the expense of helium. So the simplest interpretation is that the Lyman continuum, the diffuse Lyman continuum in galaxies actually, whenever there's any photon above the helium edge, it degrades back into being a Lyman for hydrogen. It's not an obvious, it's probably a correct inference, but the explanation is not obvious. Okay, but the JWST observations that we had for from sulfur 3 to that's why, sorry, this mixed up. This also,
That is not obvious. And so if it's softening, is it heating then in certain regions? Like, do you have some excess unaccounted for heat that then explains that in like dense regions or something?
I think this is actually a kind of a problem where you have to really simulate. I think what's happening, okay.
Listen to you.
Because it's not an analytical calculation. I've thought a bit about it, but we can discuss that a little later. It's actually a very simple problem but I believe we should simulate this now. Okay, and it's a competition between that photon, whether you can ionize helium. New found theories. I tried to do this analytically and I got the wrong answer. That means it's time to do the simulations. Okay, so I'll come back to this. Oops. Okay, I got this mixed up. So conclusion from the JWST observations. One is we can detect it's easy to detect neon 2 from anywhere in the galaxy, no matter where you point to. Okay. And so the region that what we saw is not from a tiny H2 region, but in fact, it's a diffuse gas because we see it in 2 different locations. And also tiny H2 regions do not have emission measure of 1. That's a very strange H2 region. And the fact that now we can do this ratio, that means neon plus is the dominant species. It tells me that the radiation field is not very hard. Okay. Of course, there's only one line of sight, but I'm just saying this is what you'll start doing. But the most interesting one is the sulfur 3 to neon 2. Okay. That suggests to me the rapid fall off in ionization with increasing energy. So I would say that there are 2 different lines of one is the radio recombination lines. And if you believe this is indicative of future JWST results, this is a huge extrapolation based on the first observation. But I sort of already am biased because I think I know the radio answer, is that we are looking at a field that is actually very, the radiation field is soft in my mind. Okay, no matter what you put in with the hard sources, it degrades and just becomes capable of ionizing only hydrogen, or it's at the expense of helium. Okay, so forward. There's some really fun things you can do. So this got me thinking a bit about. I was actually really astonished that if I had not done the calculation and if you asked me 3 by 3 arcsecond, would you see diffuse emission? I'd have told you surely not. Okay, but that's the power of large A. So that made me think a bit, okay, there's a new, there's optical IFUs that are coming along. I mean, one of the best IFUs is Muse, but there's another one coming, which is KC, the Keck Cosmic Imager. The primary difference between these two, Muse is really fantastic. It is a very large grasp, but Muse doesn't have high spectral resolution. And in this game, that is the key. But with Keck Cosmic Web Imager, you really can actually get a resolution approaching 20,000 and an IFU at the same time. That's really stunning, actually. So this, and it's the PI for this is my old buddy and our buddy, Chris Martin. We are all classmates, Mike, Chris, and I. So anyway, I told Chris, I called him up. I said, okay, well, it's got a reasonable field of view. I said, okay, Chris, I have some. As soon as you see first light, let's go and bang away and write a quick Nature paper or something like that. And he's all excited. So this should be an easy paper to write. Okay, because the calculations show with an hour of KCI integration, with only 1 arcsecond, these are the SNRs you'd see through all these optical lines. It's really amazing. Again, if you're not into this sort of stuff, to see such high signal to noise ratios. Okay, so at one end you have this new development like Dragonfly, and the other end you have this other development where you can really now start seeing stuff on arcsecond scales. Okay, and I'm very excited about those possibilities. Okay, so here's my forecast. Any hour-long observation of medium MRS is grist for the WIM mill. Okay, and you'll see all these lines actually, because the minimum SNR in this game is about 10. But you have to reduce this, you have to learn how to reduce the JWST IFU data to photon limited thing. It'll take a while. The new IFUs in particular, I don't know what VLA, it's a VLT actually. New IFUs and large telescopes are also, again, when Chris and company want to go and look at some Lyman alpha blobs from Redshift 1 or Redshift 0.1 or something, I told him, no matter what, this is I'll get my ISM observations right away out of that. So you could have exactly the same program on the ground-based system as on JWST. One of the things I think that can be done is to really not waste any more time with oxygen 1, but to use nitrogen 1 to measure directly. And this can be done, it's very nice, 50 to 100 angstroms, right where the whole system peaks actually. The other stuff is you can really start, the power of this instrument is so large, you really can start studying the WM arcsecond scales, which again, if you had asked me in June, I would have said, no, that seems, yeah.
Well, what's the resolution you can have with a long line of sight?
What's that?
What sort of resolution they would have a long line of sight?
What do you mean along the line of sight?
Well, it says of picking out discrete structures.
In velocity?
Well, no, I mean, well, we know
from pulsar scintillation. And so to what extent,
Oh, those are there, those are very tiny structures. Yeah. Okay.
tiny for
Tiny for this. Okay. Okay. So I think this will be a sort of thing you'll get for free, actually. And the other thing that is fun, and sort of trying to talk Martin into this, is most people haven't really studied tiny nebulae. For example, you could ask the question: there are many A stars, 10,000 Kelvin, right? Some of them will be in the core neutral medium. About 3%, in fact, of them will be in that. They'll have little astronomical spheres, and we have not studied them. But I think with these instruments, you can start studying these things. And in fact, on the other hand, you can have a white dwarf, and that is a little high temperature. You can take a 20,000 Kelvin white dwarf and put it in the warm neutral medium. It also should have a astronomical sphere, which is detectable by these instruments. In fact, if you study enough of them, you can turn around and get this one number, which is the filling factor of the warm neutral medium, which we only infer but not measure. So I would say this is somewhat exciting. At the other end, of course, you all know there's Chaz, Dragonfly version 2. They're on the detecting of, if you go at a somewhat higher redshift, they're all poised to do this detection. Okay, so I think that's about it.
Can I ask whether students in the seminar room specifically have any questions? Like,
Okay, I don't know a lot about the JWST, like where their pointings are going to be, but is this supposed to be a proposed project for JWST or just scavenging from every other JWST? Okay, and so random pointings and
So yeah, it's just wait till the data goes public or ask someone who's looking at high redshift galaxies and say, I'll write a paper faster than you, just give me your data.
okay. How much of the sky are you expecting then from? Okay,
Not much. It's just JW, as long as it continues, every pointing more than an hour, which is quite a bit actually, because a lot of the deep extragalactic studies it is designed for this medium MRS system. I would say probably 10-20% of JWST time will probably use this mode. That's my guess. But they're the same with other IFUs. Because someone would have figured the two lower spectral resolution to be interesting. But with the Keck cosmic image, I think this will be a little cottage industry.
Any students or postdocs in the room or online are welcome to ask questions.
So you mentioned that the WIM is a significant contribution to the total disk and the galaxy as a whole. Is it how concentrated is it overall in the disk, or is it more halo structured?
Not paid much attention, but I would naively think it just simply follows the star formation, UV.
Because I guess if you're using JWST data that's small field, then that would depend on what part of the sky you're looking at, right?
Yeah, the observation showed is more or less at like latitude of 60 degrees, nothing special. So you don't have to worry. Most of these will all be nearby that you're doing. In the plane, it'll be a mess because you'll see very bright signal, and it's not, that's some advantage. It'll actually have less. Curiously, it'll have these mid-infrared lines are nice because the extinction will be essentially a non-issue. And also, unlike optical lines, which are temperature sensitive, these are temperature insensitive because even at 20 microns, it's maybe only 1,000 Kelvin, so very sensitive to the actual temperature of the WIM. So in that sense, they're useful.
Okay, thanks.
I'll open up questions to everyone in the room.
Martin. Constraint on the neutral fraction from the fact that we don't see a alpha nebula around Gauss-Schopf around 20 pulsars. Always the idea was, they're in the warm ionized medium, therefore we see them. But if it was really 50%, we would see, I think, H alpha nebulae around all of them.
It is, yeah, I would say that's true. That's true.
I got it. I wasn't clear. I infer the spectrum shift using H2 region observations, and that there's no information.
Hard range to get to. The EV optical depth from, I think, was dominated compared to hydrogen, but let's say it's comparable. So, but the question is not so. Even if you measure the inside, if you measure the inside, in some sense, that the ionized gas. You want to know what is that? The ionized gas. You want to know what is the inside, or in the diffuse medium, and what happens. So the problem is somewhat easy to. It's easy to state. Is obviously in the details here. We know that most of the Lyman continuum, well, we believe that most of the Lyman continuum in galaxies comes from massive stuff, OB associations and so that and what fraction leaks out. We now know that out. And in order to explain this, the inference is a sixth. Okay, and so there are many projects aimed at measuring, in some sense, the leakage from H2 regions, and they won't disagree with it. Maybe it could be a quarter, but I would. It's not 90% leaking out. That's, you know, H2 regions look fairly sharply bounded. Okay, so the first one is what fraction. The second one is if we start off with the average radiation field of these from these hot stars, as it propagates through partially ionized gas, it will get modified. We know that. And if you just do it in a very simple-minded way, if you make it homogeneous, which you can then do analytically, you find the answers completely makes no sense. Then you can play some games. You can put some tunnels and holes or quote unquote fractal, and then you can get some things. But you know, it's a little unsatisfactory because you're not very sure. It's nice to say the ISM is fractal, but such a theoretical concept. It surely is a mathematical crutch. It's not a real thing. So at this point, you can go and directly measure. And all I'm saying is, right now it appears to me the totality of this evidence. But you know, we'll know in another year or two with KCI and JWST data, this will get measured. Okay, I'm saying likely it appears to me that the radiation field would start off with photons above the helium edge, but as they propagate, they get degraded and roughly between below the helium edge and hydrogen. How this is where I would say you really have to, you know, do this as a simulation at this point.
So can I add to, back, you may remember like in prehistory when we were young, I was searching for new H2 regions, right? And one of the things I did was I pulled out a catalog of about 1,000 O and B stars and looked for the H2 regions associated with them and didn't find any, except for the ones that we already knew about. So most O and B stars in the standard catalog do not have an associated H2 region. Well, because when they're dense clusters, they're in young things, they stand out and you see the H2 region. So there's these very, very familiar ones. But if you just go to a catalog of OB stars, 1,000 stars, you'll find you can't figure out which H2 region they're associated. They're just out there somewhere. You can't find the H2 region. There's just diffuse H alpha everywhere, but there's no H2 region identifiable with it. It's weird. Yeah.
If we don't have questions in the room, I'd like to open up questions to the online audience. Does the online audience have questions? Okay, Chris.
Is this going to help at all refining our galactic any distribution for FRB research?
Again?
It's going to help at all refining our galactic any distribution for FRB research?
I never take that stuff very seriously. So you're asking the wrong guy. I don't take any, you know, these things. It's a thing you just, it's roughly the place to it is the place to it is 23 centimeter minus 3 parsec. Now, you put the latitude, that's all that is to it. Sing around with, I say this to my friend Jim Cordes, who's my host at Cornell, just so you know, and he's still my friend. So I think this is the reality is that the ISM is very, very patchy. And even the idea that you can actually characterize the WIM by the single temperature and a single ionization, let alone a structure function, which, you know, may vary. So these sorts of things, you have to have a certain relaxed view of the universe. So I won't worry too much about the any 2020 or any 2000, but that's my view.
More interesting though. And I mean, in particular, when you're trying to, well, how does this, we've got these cosmological hydrodynamic calculations that are, increasingly sophisticated and increasingly degenerate on these small scales. I mean, this was kind of the reason that we undertook the local volume mapper, which I note you're not interested in. But I mean, it will do exactly this.
Asked Juna, can I join the LVM science meetings? And she demanded that I become a member,
What are you talking about? Shri, by the way, was the first investor in the SDSS-5 project. So I think
Juna sent a note at 9 p.m. and by 11 p.m. I committed $10,000 of my own money to help her the project.
but
By the way,
but I do think that, I do think in general, the way that we can compare galaxies to simulated galaxies, because a galaxy is a thing with these like few properties that you measure. But when you want to compare the gas, right? I don't think that we're very sophisticated theoretically in how we're planning, how we are actually approaching that problem. So even something like, just the different PDFs that you use to describe the ISM, right, are just very rudimentary. And so I think there's a big sort of intellectual area here to figure that out, even though it's pretty messy. So it's not going to be a nice Schechter function or something, but it's going to be some other thing that's interesting. I think there's some exciting opportunity for organizing this. I don't know if you guys would agree with that. You ISM folks in the room. Well, on that skeptical note, I'm hopeful.
Okay, on that hopeful note, let's thanks Shri again.